Welcome to this explainer, where we're unpacking India's historic leap in aerospace propulsion and exactly what it means for global defense. Today we're looking at a milestone that might honestly seem like just another defense headline at first glance, but when you look closely at the hardware involved, it represents a massive shift in international military capabilities.
So why is building a jet engine so notoriously difficult? Well, we're starting with this question because it really sets the stage for everything we're going to discuss today. Mastering jet engine technology is widely regarded as one of the most sophisticated engineering disciplines on the planet. It requires extreme, microscopic precision, highly advanced metallurgy to withstand insane temperatures, and uncompromising manufacturing standards. Because of all this, it's an elite capability that only a handful of nations in the entire world have successfully achieved. It's a very exclusive club, and the barrier to entry is astronomical.
Okay, here's our roadmap for today. We'll quickly cover the jet engine challenge, meet the ATGG engine, see how it powers the NASM, look at the anatomy of the missile, and finally discuss why this is a strategic turning point.
Part 1, the jet engine challenge. There is a massive difference between having an engine on paper, like your blueprints, theories, and calculations, and having an engine actually built in metal. Bridging the distance between a brilliant design and actual running, precision-engineered hardware has honestly been the country's most stubborn defense technology problem. You can run all the calculations you want, but actually forging the alloys and machining the parts to tolerate the extreme stresses of jet propulsion, that's a monumental hurdle. But, as we're about to see, that hurdle has officially been cleared.
All right, Part 2. Meet the ATGG engine.
What's really fascinating here is exactly how the stubborn problem was solved through an incredible public-private partnership. The design was held by DRDO's Gas Turbine Research Establishment, or GTRE. But to turn those designs into a physical reality, they partnered with Azad Engineering over in Hyderabad. Azad handled the uncompromising manufacturing and assembly, which culminated in a historic delivery on July 22, 2026. And this isn't just some prototype. It's the Advanced Turbo Gas Generator, or ATGG. Specifically, it's a single-spool expendable turbojet engine.
Now keep this number in mind, 350. This represents the thrust class in kilograms for this specific engine. A 350-kilogram thrust class means we're looking at a highly compact, lightweight, but incredibly powerful piece of indigenous machinery designed to propel things very fast over long distances.
So the crucial takeaway is how these specific components work together to deliver a high thrust-to-weight ratio without all the added weight and complexity of cooling systems. Air is violently compressed through a 4-stage axial flow compressor. Then it's mixed with fuel and ignited in the annular combustor. All that massive energy spins a single-stage uncooled turbine. And actually, the fact that it is uncooled is pretty amazing. It means the metallurgy is so advanced that it can withstand extreme exhaust heat all on its own. Finally, it's blasted out of a fixed exit area nozzle to optimize the thrust. It really is a masterpiece of compact efficiency.
Let's move on to Part 3, powering the NASM. So this ATG engine isn't just a science experiment designed to sit in a lab somewhere. It's going to serve as the long-term production power plant for the NASM. That's the Naval Anti-Ship Missile medium range. This is an all-weather, over-the-horizon missile developed by DRDO specifically for the Indian Navy to neutralize major surface combatants, like enemy frigates and destroyers. To give you some context on its capability, it is widely considered to be in the exact same class as the famous U.S. Harpoon missile.
Point 9, that is the Mach speed this engine will propel the missile at. Flying right under the speed of sound at Mach 0.9, the NASM uses a tactic called sea skimming. It literally flies incredibly close to the surface of the ocean, hiding it below the horizon line of enemy radar until the very last second. That makes it incredibly difficult for a warship to detect and intercept in time.
Part 4, anatomy of the missile. Let's zoom out a bit and look at what that 350-kilogram thrust engine is actually pushing through the air. The ASM weighs 600 kilograms, measures 5.2 meters long, with a diameter of 480 millimeters, and it's armed with a devastating 150-kilogram penetration, cum blast, or PCB, warhead. Basically, it's designed to punch right through the thick steel hull of a warship before detonating inside. To get there, the mid-course guidance relies on inertial navigation, satellite systems, and a radar altimeter to maintain that low sea-skimming height. And for the final kill, it switches on its own active radar homing system to lock onto the target for terminal impact.
What's really brilliant here is the versatility of the missile program. It's not just a one-trick pony.
The air-launched variant can be fired from a Tejas, a MiG-29K, or a P-8I, reaching targets up to 290 kilometers away with no additional booster. But if you launch it from a surface warship, it gets an extra solid fuel booster to push its range to 350 kilometers. There's even a submarine-launched variant that reaches over 100 kilometers, also using that solid fuel booster. It just shows how different launch environments dictate the range in engineering while all relying on that core turbojet technology.
Finally, Part 5. A strategic turning point.
The Ministry of Defense really captured the true essence of this milestone, stating it marks the culmination of years of precision engineering, advanced manufacturing, and close partnership between India's scientific and industrial communities. Defense Secretary Rajesh Kumar Singh specifically complimented this exact synergy. A government lab drew it up, but private industry turned it into reality. It perfectly aligns with the vision of an Aatmanirbhar Bharat, a self-reliant India. It proves that the domestic industrial base totally has the chops to handle the world's most demanding engineering disciplines.
So what's the big takeaway? The implications here are twofold. First, by mastering this technology indigenously, India secures its own defense needs. They no longer have to rely on foreign suppliers for critical propulsion systems. But secondly, and maybe more importantly for the global market, it opens the door to exports. When you can build reliable, highly capable turbojet engines internally, you suddenly transition from being a massive defense importer to a highly competitive seller on the world stage.
So, I want to leave you with this final thought. Could this single 350-kilogram thrust engine permanently alter the balance of the global defense export market? It is wild to think about how a microscopic engineering achievement, an engine roughly the size of a large duffel bag, could ripple out to reshape the entire landscape of international defense dynamics. Thank you so much for joining me for this explainer, and keep exploring the incredible mechanics behind the news.